गुड आफ्टरनून बच्चों। स्क्रीन विजिबल है सबको?
यस सर।
Yes, sir.
ओके ओके। So basically you're talking about chemistry paper 2 module number 1, that is alkyl and aryl halide. In IUPAC this alkyl halide is called as haloalkane. Okay, so at the beginning we'll revise how by replacement of one hydrogen of alkane. If you replace one hydrogen of alkane by one halogen atom, you will get the compound that called as alkyl halide, and in IUPAC it is called as a haloalkane. Now the homologous series of the haloalkane is, or your haloalkane having the general formula CnH2n1 plus X. So this is basically derived from the alkane by replacement of one hydrogen atom of alkane by one halogen atom. Okay, so this is the general formula of haloalkane. Now again, most of the haloalkanes are toxic and highly carcinogenic in nature. Nomenclature related to IUPAC nomenclature, the way of naming the haloalkane is similar to way of alkane. First, you need to find out the longest possible carbon chain that contain what? Single halogen atom, or that contain a halogen atom. So, okay, then find out the branch alkyl and halogen present, and your halogen and your substituent must get to which number? Lowest number. Okay. Next is the classification of your haloalkanes and haloarine. The haloalkanes and haloarines are classified on the basis of the number of halogen atom. Okay, they are classified as mono, di, or polyhalogen. In the polyhalogen, it is further classified as tri, tetra, etc. Okay, tri correspond to 3, tetra correspond to 4, depending on the whether they contain 1, 2, or more halogen atom. Okay, for example, this haloalkane and haloarine are classified as monohalo because this compound contains single halogen. Now it is classified as a dihalo because it contains two halogen atom. Now this is a trihalo because it contains three halogen atom. So these are the monohaloalkane, dihaloalkane, and trihaloalkane. Next is the monohaloarine. Why this is a monohaloarine? Because it contains single halogen present on the benzene ring. This is a dihalo. This is a trihaloarine. Okay. Now the monohalo compounds further classified according to the habitation of the carbon atom to which the halogen is bonded. What is the further classification? We are talking about the mainly monohalo compound. In our syllabus, we are basically going monohalo compound. Okay, and this monohalo is further classified according to the habitation of the carbon atom to which the halogen is bonded. Okay, and they are discussed as follows. In this case, compounds containing sp3 hybridized carbon atom on which the halogen is attached. So basically, halogen is attached to your singly bonded carbon. That is nothing but the sp3 hybridized carbon. And this class includes, or this classified as follows: alkyl halide or haloalkane. In alkyl halide, all of you know that they have in the general formula CnH2n plus 1. This alkyl halide is further classified as primary, secondary, and tertiary. Okay, according to what? Nature of the carbon to which the halogen is attached. So basically, this is a primary alkyl halide. Why? Because halogen is attached to the primary carbon. Sir, what is the primary carbon? The carbon which is attached to another one carbon atom. Okay. Now this is a secondary alkyl halide because halogen is attached to the secondary carbon. Why this is a secondary carbon? Because this carbon is attached to two other carbon atom. Now realize halogen is attached to carbon, that carbon is attached to three other carbon atom. So this is the alkyl halide classification as a primary, secondary, and tertiary. Now next is the allylic halide. Okay, in which the halogen is attached to sp3 hybridized carbon atom, and that sp3 hybridized carbon atom is attached to what? Your carbon-carbon double bond. Okay, that is called as the allyl halide. Halogen is attached to sp3 hybridized carbon atom, and that sp3 hybridized carbon atom is attached to what? Carbon-carbon double bond. That is called as a allylic halide. Now next is halide. These are the compound in which the halogen atom is bonded to what? sp3 hybridized carbon atom next to what? Aromatic ring. Halogen is attached to carbon, that carbon is attached to what? Aromatic or benzene ring, then it is called as a benzylic halide. Okay? What is the benzyl group? Basically, benzene ring and CH2 is called as a benzyl. Next classification in which halogen is attached to what? Your sp2 hybridized carbon atom. Now in this under this class classified as phenylic halide and aryl halide. So in case of the phenylic halide, halogen is directly attached to your carbon carbon double bond. You can see here halogen is directly attached to your carbon carbon double bond. Okay, similar way here halogen is directly attached to your carbon carbon double bond. This comes under the category of phenyl halide. Next, in case of the aryl halide, these are the compound in which halogen is directly attached to what? Directly attached to aromatic ring. In this case, this halogen is directly attached to the aromatic ring. That will come under the category of aryl halide. This is another aryl halide, or you can call aryl halide, in which halogen is directly also attached to the aromatic ring. So these two compounds come under the aryl halide. What is the basic difference between the alkyl halide and aryl halide? In case of the alkyl halide, your halogen is attached to the alkyl group, and in case of the aryl halide, halogen is directly attached to aromatic ring. Okay, once the classification is complete, now we'll discuss about the nomenclature. So in case of the common name, it is called as alkyl halide, and in case of the IUPAC, it is called as what? Haloalkane. So in case of the common name, it is alkyl halide, and in case of the IUPAC, it is called as what? Haloalkane. Okay. So this is what 3 carbon, therefore it is a N propyl bromide as per the common name. N is nothing but a normal or straight chain, therefore it is a N propyl bromide. As per the IUPAC, it will be the bromine is attached to first carbon, therefore it is a 1 bromo propane. What about the next compound? It will be the isopropyl chloride, and IUPAC name will be 2-chloro. Okay. What about the next compound? It is the isobutyl chloride, which is a common name. What is the IUPAC name? 1-chloro 2-methyl propane. I'm not going to in detail about the longest chain selection and all these things. We already discussed this in the this semester as well as in the previous semester in IUPAC. Okay. Now next about the IUPAC nomenclature of your haloarine. The haloarines are the common as well as the IUPAC name of the aryl halides. Okay. So this is a bromobenzene, as the bromine is attached to the benzene, common name and other same. This is what meta-dibromobenzene. In common name, it is called the meta. Relationship between these two bromine are 1, 3. Therefore, it is called the meta-dibromobenzene. In IUPAC, you can call as 1,3. तो मेटा को क्या बोला जाता है? 1,3. और तो रहेगा तो 1,2. पैरा रहेगा तो 1,4. In common name, you are using the prefixes ortho meta para. In IUPAC, you are using the numbering instead of this ortho meta para. For ortho, the numbering is 1, 2. For meta, numbering is 3. For para, numbering is 1, 4. Okay. Now next is a symmetrical tribromobenzene, and in IUPAC you can give the numbering like this way: 1, 2, 3, 4, and 5. That is a 1, 3, 5 tribromobenzene. These are the IUPAC name of the some compounds. Okay, you can try the IUPAC name of this compound. I already given this homework. Okay, in this semester, you can try this. Okay, IUPAC name of this compound. They have given the structure as well as the common name and IUPAC name. So you can go through this. You will get the more idea related to IUPAC and common name of alkyl and aryl halides. Now next is the nature of the carbon halogen bond. In case of the alkyl halide, your carbon and halogen bond is a polar bond. Since the halogen atom is a more electronegative as compared to carbon, therefore your halogen carries delta negative. Delta is negative, is nothing but the partial negative, and your carbon carries partial positive charge. Because of the difference in the electronegativity, okay, your carbon carries partial positive charge and partial negative charge. Since the size of the halogen atom increases as you go down the group in the periodic table, fluorine is the what? Smallest than the iodine. Okay. The carbon halogen bond length also increases from the what? Fluorine to, that means carbon fluorine to carbon iodide. You can see in this table. Okay. Bond length is increases as you increase or as you go from the fluorine to iodide in the periodic table. Okay. Size of the halogen is also increases, and bond enthalpy goes on decrease. That means you can easily break your carbon iodide bond as compared to carbon fluorine bond. Lesser the bond length, stronger is the bond. Okay. Next is the method of preparation of alkyl halide from the alcohol. We can discuss that there are different methods for the preparation of alkyl halide. Okay, so basically in the first we'll discuss from the alcohol. You can treat the alcohol with hydrogen acid such as HCl, HBr, HI in presence of the your catalyst such as ZnCl2. Okay, if I treat the alcohol with the HCl in presence of ZnCl2, that is called as the Lucas reagent, I can convert this OH into what? Halogen. I will get the alkyl halide and water is the byproduct. Similar way, I can treat this alcohol with the HBr, but the problem with the HBr is the HBr is an unstable compound. Therefore, it is prepared from what? Sodium bromide and sulfuric acid. That is two preparation. So combination of the sodium bromide and sulfuric acid gives me what? Gives me HBr. And the form HBr react with my alcohol to get the alkyl bromide. Okay. Similar way, I can prepare alkyl chloride by the reaction of the alcohol with the phosphorus trichloride, PCl3. In that case, I can replace this 3OH by the 3 halogen to get the alkyl halide, and the byproduct is H3PO3. Similar way, I can treat the alcohol with the PCl5, that is called the phosphorus pentachloride, and byproduct is POCl3, that is the phosphorus oxychloride and HCl. Okay. In case of the your PCl, PBr3 and PI3, as this PBr3 and PI3 are unstable compound, you can prepare this PBr3 and PI3 compound in C2 by the reaction of the red phosphorus with the corresponding halogen. Okay. So in that case, you will get the PBr3 in C2 and PI3 in C2. That form PBr3 and PI3 react with the alcohol to form the corresponding alkyl bromide alkyl halide compound. Okay. Similar way, you can treat the alcohol with the SOCl2, that is called the thionyl chloride. In that case, OH is replaced by the Cl, and the byproduct form are gases, that is the SO2 and HCl. Therefore, out of this different method for the preparation of your alkyl chloride, which are the different methods, such as the reaction of the alcohol with the hydrogen chloride, then the reaction of alcohol with the PCl3, reaction of alcohol with the PCl5, reaction of the alcohol with the thionyl chloride. All these methods gives me alkyl chloride, but the best method is the thionyl chloride because the both the byproduct form are gases in nature. Now next is the preparation of your aryl halide by the electrophilic substitution reactions. So you can prepare your aryl halide, or basically your aryl chlorides and bromides are easily prepared by the electrophilic substitutions of your aryl with the chlorine and bromine respectively in the presence of what? Lewis acid catalysts such as iron or iron chloride. So in this case, if I take here chlorine, I can use the catalyst such as AlCl3. If I take here bromine, I can use the catalyst such as FeB. In that case, we will get the two product. As this methyl group is the electron donating group, I will get the two product. One is that halogen at ortho position, and in another case, halogen at the para position. So out of this ortho and para is the major product. Okay, this is the ortho halotoluene and this is the para halotoluene. So basically, we are preparing or we are adding the halogen to the benzene ring by the electrophilic substitution reactions. Okay. The ortho and para isomer can be easily separated due to the large difference in what? Their melting point. And you can with the iodine in this case, instead of your chlorine and bromine, you can do the iodination reaction. But remember that your iodination reactions are what? Reversible reaction because of the formation of HI in the reaction, and you can avoid that reversible reaction by adding the oxidizing agents such as HNO3 and HiO4. Okay. We cannot prepare the fluoro compound by this method as the fluorine is a highly reactive compound. So this is about the electrophilic substitutions or preparation of your aryl chlorides and bromine. Now next is the Steinway reaction. It's a very important reaction. This is a for the primary amine, aromatic primary amine. When an aromatic primary amine dissolved or suspended in or when aromatic primary amine react with the NaNO2, that is called the sodium nitrite in presence of your hydrogen halide. So basically from this I will get the byproduct NaX, and what is the remaining from this? HNO2. Okay, HNO2. That HNO2 is called what? Nitrous acid. Okay, in this case, if I take here HNO3 is a nitric acid, acid. As in nitrous acid is unstable, okay, therefore it is prepared by the reaction of the sodium nitrate and hydrogen halide. So that nitrous acid will convert my NH2 group into what? N2 plus and X minus. That is the benzene diazonium halide. Remember that primary aromatic amine on the reaction of the sodium nitride and hydrogen halide at lower temperature, which is a lower temperature 0 to 5 degrees Celsius, it will convert into the benzene diazonium halide. Okay, this reaction is carried out at a lower temperature because temperature only this benzene diazonium halide is stable. Okay, once you will get the benzene diazonium halide, that benzene diazonium halide react with your cuprous halide such as cuprous chloride, cuprous bromide. We will get the corresponding halide. If I use a cuprous chloride, I will get the chlorobenzene. If I use a cuprous bromide, I will get the bromobenzene. Similar way, you can prepare the iodobenzene by the from the benzene diazonium halide by simply adding potassium iodide into this. Okay, so we will get the iodobenzene, and the byproduct is nitrogen gas. That is about the Sandwich reaction. Now we'll next discuss about the preparation of different alkyl halides from the alkenes. So in that case, you can prepare alkyl halide from alkene by simply adding the hydrogen halide to the alkene. This is a hydrogen halide I am going to add towards the alkene. Now this is a symmetrical alkene. Therefore, I will get the only one product. There is no issue. I can add this hydrogen to the left hand side, or I can add the hydrogen to the left hand side. Okay, we will get the only one product. But remember that when I am using the unsymmetrical alkene, this is unsymmetrical alkene. Across the carbon-carbon double bond, both the sides are different. Okay, and I am adding the hydrogen halides such as HCl, HBr, HI. In that case, I will get the two products. Okay, one will be major, another will be minor, and this major and minor product is decided on the basis of the Markovnikov's rule. What the Markovnikov's rule says that when an unsymmetrical, what is the Markovnikov's rule? What is the Markovnikov's rule? In an addition reaction, the negative part of the unsymmetrical reagent must attach to that carbon, that unsaturated carbon, which carries less number of hydrogen atom. That means basically my I minus must attach to which side? A side or B side? I minus must attach to the A side. Okay, in case of the major product, because A carries less number of hydrogen atom. Okay, this is about the Markovnikov's rule. In case of the in case of the anti-Markovnikov, negative part must attach to that unsaturated carbon, which carries what? More number of hydrogen atom. Okay, so here you get this as a minor product, that is one iodopropane, and two iodopropane as a major product. So this is about the Markovnikov's and anti-Markovnikov's rule. Anti-Markovnikov's rule generally take place in presence of the peroxides such as H2O2. Next is the addition of halogen. You can add your halogen. This is a not this is a symmetrical reagent. Therefore, in this case, you will get only one product. Okay. What is the Markovnikov's rule? When your reagent and your alkene both are unsymmetrical, in that case, it is a Markovnikov's rule. Okay. Out of this, your one compound, that is your reagent or your alkene is a symmetrical. In that case, there is no Markovnikov's rule involved. You get only one product. In this case, my alkene is symmetrical, my bromine is also symmetrical reagent. Therefore, if I add this bromine across your carbon-carbon double bond, I will get the vicinal dibromo compound, or you can call as 1,2 dibromoethane. Okay. Addition of bromine in presence of your carbon tetrachloride as a solvent, resulting in what? Resulting in a discharge of reddish brown color of your bromine. And this is the important method for the detection of what? Your double bond in a molecule. You can try these examples at home. Okay. In this case, you are going to add HBr across the carbon-carbon double bond where the Br must attach. Br must attach to the left hand side or right hand side. Br must attach to the left hand side because side carbon contain one hydrogen. Okay. Next, yes, in case of the HCl, Cl must attach to the left hand side carbon or right hand side carbon. Cl must attach to the left hand side carbon or this carbon. Why? Because it contains one hydrogen atom. Next is HBr in presence of the peroxide. In that case, what happens? Br must attach to what? That unsaturated carbon which carries more number of hydrogen atom. So Br must attach to the CH2. Okay, it is very very simple. You can try. Next is halogen exchange reaction type. Preparation of your alkyl iodide compounds and your alkyl fluoride compounds are difficult because your iodination reactions are reversible reaction and your fluorination reactions are too fast. Therefore, it is a you can call as explosive in nature. Therefore, generally alkyl iodide and alkyl fluoride compounds are prepared by the halogen exchange. So basically, you can prepare your alkyl iodide and alkyl fluoride compound from the corresponding alkyl chloride and alkyl bromide compound. So, for example, alkyl chloride compound, and in that I am going to add sodium iodide. So basically, this halogen chlorine is going to replace by the iodide. So I will get the alkyl iodide, and byproduct will be NX. So preparation of alkyl iodide compound is called the Finkelstein reaction. Okay. Next, alkyl corresponding alkyl chloride or bromide compound on the treatment with the metallic fluoride. As these metallic fluorides are stable compound, you can treat the corresponding alkyl chloride or bromide with a different metallic fluoride. In this case, this Br is replaced by the fluorine to get the alkyl fluoride, and the byproduct will be HBr. Different metallic fluorides such as AgF, mercury fluoride, cobalt fluoride, antimony fluoride, these are the used. And the preparation of your alkyl fluoride compound is which reaction? Schwarz reaction. Next is the chemical reaction. Reactions of haloalkane. Chemical property. You can say that the reactions of haloalkane may be divided into the following categories. First is the nucleophilic substitution reaction. Next is elimination reaction. Third is reaction with metal. So first we will discuss elimination reaction. So in case of your alkyl halide, this carbon carries partial positive charge and halogen carries partial negative charge because of the difference in the electronegativity. Therefore, the coming nucleophile will easily approach this carbon. So therefore, this alkyl halide will undergoes nucleophilic substitution reactions. Why coming nucleophile will approach this carbon? Because nucleophile is a negatively charged species. You will get the nucleophilic substitution reaction. Okay? So substitution reaction takes place, and halogen basically in case of the nucleophilic substitution, your halogen is going to replace. So halogen is called the living group, the group which goes out, that is and the substitution reaction is initiated by nucleophile. Therefore, it is called the nucleophilic substitution reaction. Okay. So in this case, you can discuss the different nucleophilic substitutions such as this ethyl bromide in presence of aqueous NaOH or KOH. This is the Na plus and your OH minus. My nucleophile will be OH minus. OH minus will attach or attack on the carbon. Okay, having the halogen attached. So OH minus will attack the carbon group. Okay, having the halogen atom. OH minus will approach. Same time, this halogen will depart. So you will get what? Alcohol. You can convert your alkyl halide compound into the alcohol by the treatment with the aqueous alkalis. Okay. In this case, the role of the solvent is very very important. If you use the aqueous alkali, we will get the substitution product. If you use the alcoholic alkali in this instead of NaOH, if you use sorry instead of your aqueous solvent, if you use the alcoholic solvent, in that case elimination will take place. Okay, we are going to discuss that in the next slide. Next is the reaction of alkyl bromide with the KCl. What is the nucleophile in case of the KCl? K plus and Cn minus. The Cn minus will attack on my carbon, and the Br will depart. So I will get the nitrile compound. That is the propane nitrile compound will be formed. This is very simple. You need to replace that halogen by the coming nucleophile. And what is the use of this cyanation reaction, or what is the use of this reaction of your alkyl with the KCl? In case of your cyanation reaction, it extends the carbon chain. So basically, we will get the one extra carbon from the cyanide group, and that one extra carbon can be converted into the variety of functional group. So cyanide can be converted into the what? Carboxylic acid by the hydrolysis reaction. Okay, cyanide can be converted into the primary amine by the reduction reaction. Okay, cyanide can be also converted into the amide by the incomplete hydrolysis. Yeah, you can call it a partial hydrolysis. So these are the some application of the CN group. Therefore, we are converting our alkyl nitrile compound or cyanide compound. Next is reaction of alkyl halide with the excess of ammonia. Okay, we'll get the primary amine. So basically, what's the first reaction? It involves the two steps. Alkyl halide, that is ethyl bromide, in this case react with the ammonia to form what? Ethyl amine, and byproduct will be HBr. The form byproduct HBr react with the excess of ammonia or second equivalent of the ammonia to form what? Ammonium bromide. Okay, so that is the purpose of addition of excess of ammonia. Otherwise, what happens? The form HBr in the first step will neutralize the ammonia to form ammonium bromide at this, and the yield of the reaction will be minimized. Okay, therefore, we need to add excess of ammonia for this reaction to get the primary amine. In this reaction, if you use the excess of your alkyl halide, in that case, you'll get the primary amine as a product, then secondary amine, tertiary amine, and quaternary amine. This is called the ammonolysis reaction. Okay, when you will get to use the excess of the alkyl halide. If you use the excess of the ammonia, in that case the reaction can stop at the primary amine stage. Now next is a very important table, reactions of haloalkane. So in this case we can go through this type of table. I have taken here one chloropropane reaction with what? Aqueous sodium hydroxide. In that case Cl is replaced by the OH. We will get the alcohol. Similar way we already discussed that reaction with the KCN, yeah, NaCN. In that case Br is replaced by the Cn. We will get the nitrile compound. Okay, we can replace this Br by the nucleophile ammonia to form a primary amine. Similar way, if you use the solvent, that is the ethanol, okay, ethanolic alkali such as your NaOH or KOH, in that case elimination will take place and I will get the alkene as a product. Okay, next is a Grignard reagent preparation. You can add this magnesium metal between your carbon and halogen. Okay, we'll get the alkyl magnesium halide. In this case it is a propyl magnesium halide. So this is about the reactions of haloalkane with the different reagents condition use. Now, this is a very important table with respect to nucleophilic substitution reaction. So basically, they have written here Rx and the different nucleophile. So they have given here the different nucleophile and the source of that nucleophile. Okay, because in market OH minus is not available. What is available in market? NaOH. The source of OH minus is NaOH or KOH. So basically, your Rx alkyl halide will react to the nucleophile. In NaOH, what is the nucleophile? Sir, what is the nucleophile? Basically, negatively charged species. Na plus O, that OH minus, okay, basically substitute by the X. So I will get what? Alcohol, and X minus is the byproduct. That means halide will be depart. So I will get what? ROH. That ROH is called as the alcohol. If I treat the alkyl halide with the water, so in that case my product will be what? Alcohol as well. Sir, how? When the compound having the lone pair of electron, that is also act as a nucleophile. In that case, byproduct will be HX. Okay, the compound having the lone pair of electron, in that case byproduct will be basically from the water one hydrogen, and this X from alkyl halide will be lost as a HX. So this halogen is going to replace by the OH from the water. And when my nucleophile is directly negatively charged, in that case I will simply substitute that halogen by negatively charged species. Okay, so that is a very important thing. Now in case of this sodium alkoxide, what is my species? Na plus and OR minus. That OR minus is my nucleophile. So we'll replace this halogen to get what? ROR. That is ether formation. Simply this is in this of ether. Now next, I can treat this alkyl halide with the sodium iodide. What is my nucleophile? I minus. So I will get the alkyl iodide. The preparation of alkyl iodide is which reaction? Finkelstein reaction. Next, I can treat this alkyl halide with the ammonia. I will get what? RNH2. Byproduct will be HX. So I will get the primary amine. If I treat this alkyl halide with the primary amine, I will get what? Secondary amine. Okay, and byproduct will be HX. Similar way, I can treat this alkyl halide with the secondary amine. I will get which amine? Tertiary amine. Next, I can treat this alkyl halide with the KCN. What is the nucleophile? K plus Cn minus. Cn minus is my nucleophile. I will get the alkyl cyanide and nitrile as a product. Instead of this cyanide, KCN, if I use AgCN, in that case, okay, I will get what? Isocyanide as a product. Remember that. If I use the KCN, I will get the cyanide. If I use the AgCN, I will get the isocyanide. Why isocyanide? We are going to discuss in the next slide. If I use a KNO2, I will get what? Nitrite compound. In this case, the bonding is through what? In case of the nitrite, bonding is through oxygen. If I use AgNO2, bonding is through the nitrogen. I will get the what? Nitroalkane compound. Okay. If I use a silver acetate, I will get what? Ester. If I use a lithium aluminum hydride, I will get a hydrocarbon. If I use a alkyl group with a metal, I will get the what? Higher hydrocarbons. So this is about the right now. Don't worry about the last two methods. That is not in our syllabus. Okay. So these all are nucleophilic substitution reaction. You already have discussed several times. If I use a KCN, I will get what? Cyanide and nitrile compound. If I use the AgCN, I will get the isocyanide. If I use the KNO2, I will get the nitrile compound. Yeah, sorry, I will get the nitrite compound. If I use the AgNO2, I will get the nitroalkane. Now, next question, sir. Why in case of your cyanide and why in case of the CN and why in case of your nitro compound you are getting the two product? So your cyanide and nitrites are the having two nucleophilic centers. Okay, and therefore it is called as ambidentate nucleophile. What is it? It is called ambidentate nucleophile. Okay, you do know that dented, dented. Dented is nothing but the donor side. What is it? Dented, donor side. Bidented, bi is nothing but the two donor side. Ambidented इसका मतलब क्या है? एक ही लिगैंड उसमें दो डोनर साइड रहेगा. एम्बिडेंटेड का मतलब क्या है? एक ही लिगैंड रहेगा उसमें दो डोनर साइड रहेगा. दैट इज कॉल्ड द ambidentate. Actually your cyanide group is what? Hybrid of the two contributing structures. You can draw the resonance structure. You will get the negative charge on the carbon as well as the negative charge on the nitrogen. That means a linkage can be take place through the carbon as well as the linkage can be take place through the nitrogen. If the linkage takes place through the carbon, then it will form which type of compound? Cyanide. If the linkage will take place through the nitrogen, then it will form the isocyanide. Okay. Similar way, if the linkage will take place through the what? Oxygen, then it is called the what? Alkyl nitride compound. If the linkage will take place through the, then it will form the nitroalkane as a compound. Okay, so this is about the ambidentate nucleophile cyanide and nitride. It gives the two different product. Now next question: five, your haloalkane react with the KCN to form alkyl cyanide, and with the AgCN it is forming isocyanide. Okay, so basically your KCN is which compound? Ionic compound. Therefore it provides the ion in the solution. Which are the ion? K plus and Cn minus. I will get the K plus and Cn minus. In this case, my nucleophile file is what? Carbon with the negative charge is my nucleophile. And once the carbon with the negative charge is my nucleophile, will react with my haloalkane. Okay, to form what? Nitrile compounds. Okay. In case of AgCN, as the AgCN compound is what? Covalent compound. Your Ag and carbon is not a separate compound. Okay, it is a covalent compound. So therefore, in that case, in case of AgCN, this compound can attack from the nitrogen end, and as it is attacked from the nitrogen end, as this nitrogen is electron, and therefore we will get which compound? Isocyanide. Okay, if it is attacked from the nitrogen end, we will get the isocyanide. If it is attacked from the carbon end, then you will get the cyanide. In case of the KCN, it is an ionic compound, therefore it will attack from the carbon end. In case of AgCN, it is a covalent compound, therefore what is the free? Nitrogen having the lone pair of electron is a free end, therefore it will attack from the nitrogen end and we will get the isocyanide. Now next is elimination versus substitutions. I already told you the reaction depends upon the solvent. If I use the solvent water, in that case my OH minus will act as a nucleophile and I will get the substitution mechanism and the product will be alcohol. Okay. If I use the alcohol as a solvent for your reaction, and in that case role of OH minus will be base and the mechanism will be elimination, and elimination reaction gives me alkene. तो basically इसमें से क्या याद रखना है आपको कि if I use the solvent water for NaOH or KOH, in that case I will get the alcohol as a product by the substitution reaction. If I use the solvent for my NaOH or KOH alcohol as a solvent, in that case the product will be alkene, and that alkene is formed by the elimination reaction. Okay, and other details they have written here, you can go through that detail. Okay. Now next is the mechanism. SN2 reaction. What is the SN2? S correspond to substitution, N correspond to nucleophilic, and 2 correspond to bimolecular reaction. Okay. The reaction methyl chloride with the hydroxide ion gives methanol, and this reaction follows the second order kinetics. In this reaction, the rate of reaction depends upon the concentration of what? Concentration of the both the reactant. Which are the reactant? Methyl chloride as well as the hydroxide ions. Okay. The rate of reaction depend upon the concentration of methyl chloride as well as the hydroxide ion. Therefore, here I am writing 2 because the rate of reaction depends upon the two things. Which are the two things? Both the reactant. Which are the both the reactant? One is alkyl halide, other one is hydroxide ion. Okay. Now in this case, how this mechanism will take place or how this reaction happening? OH minus is approaching. This is OH minus is approaching to the methyl chloride from the backside of your chlorine or backside of the halogen. It will approach like this way. Same time, your carbon halogen bond start breaking, and this is a TS, that is called the transition state. And once this halogen is a depart, you will get the OH. So basically, in the final product, your OH is coming from what? Opposite side of your chlorine, which is coming from the opposite side of your chlorine. Okay? This is your SN2 reaction. OH is coming from the opposite side of the chlorine. And as this OH is coming from the opposite side of your chlorine, in this case, the stereochemistry involved for this reaction is inversion of configuration. You need to remember the one word that is called the inversion of configuration. Opposite to the original, that is called the inversion. Okay. If the reactor is having the R configuration, product will get the S configuration. If the reactant is having the S configuration, product will get the R configuration. That is called the inversion of configuration. Okay. In this case, OH minus will form the bond with your carbon having the halogen. Same time, this carbon halogen bond start breaking, and you will get this type of transition state in which carbon is partially, or in this case, carbon is a pentavalent, but this carbon OH bond is a half bond, and your carbon chlorine is also half bond. Okay. Now, the next is the very important thing about the rate of reaction. Which alkyl halide will undergo the faster SN2 reaction? It basically depends upon the approach of the nucleophile. In case of the methyl halide, this nucleophile can easily approach my halogen having the, or nucleophile can be easily approach the carbon atom having the halogen. Why? Because these three hydrogen atoms are smaller in size. In case of the ethyl, I am going to replace one hydrogen by the two. In case of the isopropyl, I am going to replace the two hydrogen by the two methyl group. In case of the tertiary butyl, I am going to replace all these three hydrogen by the three methyl group. So basically what happens, I'm going from the methyl to ethyl to isopropyl to tertiary butyl. What happens in case of the tertiary butyl? There is a no space available for my nucleophile to approach this carbon having the halogen. Okay, because of the presence of the three bulkier methyl group. Therefore, tertiary butyl will not undergo your SN2 reaction. Okay, so what is the order of the SN2 reaction? Methyl halide will react faster, then the primary halide, then the secondary halide, and tertiary halide. So this is the order of your reactivity with respect to SN2 reaction. This is very important. Okay? Because of what? This order is mainly depend upon the what? Bulkier group or steric hindrance. Because of the presence of the steric hindrance in case of the tertiary butyl, its order will be, or reactivity towards SN2 reaction will be very less as compared to primary halide. Is it clear up to this point?
Yes, sir.
Yes or
Yes,
no?
sir.
ये रिवीजन इसलिए मैं ज्यादा ही फास्ट. हाँ. Next is SN1 reaction, that is the substitution nucleophilic unimolecular reaction. Okay. Generally, SN1 reactions are take place in presence of the polar protic solvents such as your water, alcohol, acetic acid. These are the polar protic solvent. Okay. Between your tertiary butyl bromide and hydroxide ion. Okay. Follows which mechanism? First order kinetics, that is SN1 reaction. In this reaction, the rate of reaction depends on the concentration of only one reactant, that is nothing but the tertiary butyl bromide. the rate of reaction is independent on the concentration of alkali, that is nothing but the OH minus. Okay, so basically what happens, this Br is going to replace by the OH to form an alcohol. SN1 reaction involves two steps. Which are the two steps? First step is a breaking of your carbon halogen bond. Carbon halogen bond, I will get what? Positively charged carbon. In this case, this positively charged carbon is which carbocation? Once I will break this carbon halogen bond, I will get the carbon with the positive charge. In this case, I am having this positively charged carbon, and that positively charged carbon is what? Carbocation. That is called the carbocation, and that carbocation is a tertiary carbocation. Why it is a tertiary carbocation? Because that positively charged carbon is attached to three other carbon or three other alkyl group. Therefore, it is a tertiary. ठीक है. SN1 occurs in the two. It is a slow step because it is a bond breaking step. Second step, OH minus will approach this positively charged carbon from the both the side, okay, front side as well as the back side, and you will get the alcohol. So step two is a bond forming, and step two is a fast step. Therefore, your hydroxide ion involved in fast step. Therefore, rate of reaction is independent on the concentration of your alkali. Okay. Two steps. First step is the bond breaking to form the carbocation. Second step, okay, this carbocation is attacked by the hydroxide ion in the step 2, which is a fast step. Therefore, rate of reaction is independent on the concentration of OH minus. Now, depending upon the stability of the carbocation, okay, your alkyl halide undergo the which mechanism? SN1 mechanism. All of you know that tertiary will form the more stabilized carbocation. Okay, tertiary alkyl undergo SN1 reaction because they has the high ability to form what? Stabilize. Okay. In summary, you can say that tertiary halide will undergo which mechanism? SN1 reaction because of the stability of the carbocation. Then secondary halide, then primary halide, and methyl halide. So this is the order for the SN1 reaction. What is the order for SN2 reaction? Methyl halide, primary halide, secondary halide, and tertiary halide. So basically, primary halide will exclusively undergo which mechanism? SN2 mechanism. Your tertiary halide will undergo which mechanism? Exclusively SN1 mechanism. And what about the secondary halide can undergo both the mechanism SN1 and SN2. It depends upon the reaction conditions. Okay? Right now, don't worry about that. Next, once this is a clear, next, your allyl halide and benzyl halide. This is the benzyl carbocation. If I put here the Cl, it is a benzyl chloride. Once the Cl will depart, I will get the benzyl carbocation. Okay. So this benzyl carbocation is stabilized because of the resonance of the benzene. Similar way, if I put here the Cl, I will get this allyl chloride. If I remove this Cl, I will get the positively charged carbon, and this positively charged carbon is stabilized because of the resonance. So basically, your allyl halide and benzyl halide, okay, undergo exclusively SN1 mechanism as benzyl and allyl carbocation are stabilized by the resonance effect. So they can ask the question in MCQ base. Okay, allyl halide or benzyl halide undergo which mechanism? Benzyl halide and allyl halide undergo exclusively SN1 mechanism. Okay, stability of the carbocation. And you know that, okay, SN1 reaction involves the which intermediate? Carbocation as the intermediate. Next is, for a given alkyl group, the reactivity of the halide, that is the alkyl halide, follow the same order in the both the mechanism. That means alkyl iodide will react faster as compared to alkyl bromide, as compared to alkyl chloride, as compared to alkyl fluoride. This is basically depend upon the living group ability. Okay, if I am having the two alkyl compound, same alkyl like methyl chloride, and I'm having the methyl iodide, faster irrespective of the mechanism, your methyl iodide, because iodide is a good living group. On the basis of this concept, they have asked the question here. So this is the which this question is, in the following pair of halogen compound, which would undergo SN2 reaction faster. So how do you find out which compound will undergo the faster SN2 reaction? For SN2, which is alkyl halide, primary alkyl halide will undergo the faster SN2 reaction. So this is the which alkyl halide? This is the which alkyl halide? Secondary. So obviously this will undergo faster SN2 reaction. Okay. What about this both are one iodo butane, sorry, both are butane compound. This is a one iodo butane and this is a one chlorobutane. So alkyl groups are in both the cases are same depending on the halogen. In this case I am having the halogen iodide, in this case I am having the halogen chloride. Which is a better living group? Iodide. So irrespective of the mechanism, iodide, this compound will undergo the faster SN2 reaction, it having the iodide as a good living group. Next is elimination reaction. Alkyl halide compound undergo the beta hydrogen. Okay, so basically this alkyl halide compound on the treatment with the your alcoholic solution. Now here it is the elimination reaction. Here I am using the alcoholic solution of your alkali, such as alcoholic potassium hydroxide, sodium hydroxide. In this case, elimination will take place. Elimination of what? Beta hydrogen. Okay, sir, what is the beta? Halogen is attached to carbon. That carbon is called as the alpha carbon. Next carbon is called as the beta carbon. Okay, and the hydrogen attached to this carbon are called as the beta. मैं फिर से रिपीट करता है, halogen is attached to that carbon. That carbon is called as the alpha carbon. Next carbon is beta carbon, and the hydrogen attached on that beta carbon are called as the beta hydrogen. ठीक है. In elimination, what happens? From the beta carbon, what is eliminated? Hydrogen is eliminated. From the alpha carbon, halogen is eliminated. Okay, as the from the beta carbon hydrogen is eliminated, this reaction is called the beta elimination. Okay, so basically from the beta, what I will lose, hydrogen is lost from the beta. So OH minus, my base is OH minus. OH minus will take this hydrogen to form what? Water. And I am going to write the double bond between the alpha and beta. Once I will write the double bond between alpha and beta, that means I will get basically alkene. Okay. Now in this case, if two different types of the beta, in that case I will get the two different alkenes. Which is a major product and which is a minor product, that can be decided on the basis of the Setzep rule. That is for the elimination reaction. So Setzep says that in dehydrohalogenation reaction, what is that reaction? Dehydrohalogenation. Now what is the meaning of the word dehydro? D is nothing but the removal. D is nothing but the removal minus hydrohalogenation. Removal of HX is nothing but dehydrohalogenation reaction. Okay, the preferred product is alkyl group having the greater number of alkyl group attached to the doubly bonded carbon. So what is the basically simple meaning of this or statement of this Setzep rule? In elimination reaction, more substituted alkene will be formed as major product. In elimination reaction, more substituted alkene will be formed as major product. Now, which is a more substituted? How will you find out? How will you find out? Here I am getting the double bond at the terminal end. On this double bond, how many alkyl groups are present? Only one alkyl group is present. Therefore, this is a mono-substituted. What about this doubly bonded? How many alkyl groups are present? Two alkyl groups are present. Therefore, it is a di-substituted. Therefore, this is a major product. More substituted alkene will be formed as major product. This is my 2-bromo pentane. This is alpha carbon. This is a beta. Okay, I can call as a beta 1. This is a beta 2. Sir, why beta 1 and beta 2? Both beta and beta 1 are same or different? Different. Why different? At right hand side, I am having the CH3 group. At left hand side, I am having the CH2 group. Both are different group. Okay. If I lose the hydrogen from the beta 1, what basically I will lose this hydrogen and this halogen. So I will get the double bond between this alpha and beta. Written here. Similar way, if I lose the hydrogen from the beta 2, what happens? I will get the double bond between these two carbons, pent2ene and pent1ene. Out of this pent1ene and pent2ene, which is a major product? Pent2ene. Okay, because it is a more substituted as per the Setzep rule. Next is the Grignard reagent preparations. Simply, in case of the Grignard reagent, magnesium metal is inserted between your carbon and halogen in presence of the dry ether as a solvent to form an alkyl magnesium halide. This alkyl magnesium halide is called as Grignard reagent. Okay, or don't worry about the other things. Next is the reactions of. Okay. बच्चे लोग समझ में आए इधर तक?
Yes, sir.
Yes, sir.
अभी और मेरे को 5 मिनट लगेगा, 5 या 7 मिनट और लगेगा। खाली एक ही मिनट देता हूँ मेरे को। स्क्रीन विजिबल है बच्चों?
Yes,
Yes,
sir.
sir.
स्क्रीन विजिबल है? हाँ। नेक्स्ट इज द रिएक्शंस ऑफ हेलोआरिन। हेलोआरिन का रिएक्शन देखते हैं, उसमें न्यूक्लियोफिलिक सब्स्टिट्यूशन फॉर द न्यूक्लियोफाइल नेगेटिवली चार्ज स्पीशीज। तो अराइल हैलाइड्स आर एक्सट्रीमली लेस reactive towards what? Nucleophilic substitution reaction due to the following reason. There are different reasons. There are 4 reasons. Your aryl halide does not undergo nucleophilic substitution reaction. Out of that, first reason is resonance effect. Okay. In haloarine, the electron pair on halogen atom, this electron pair on halogen atom are in conjugation with what? Pi electron of the benzene ring. And thus the following resonance ring structures are possible. So this lone pair of electron on the chlorine will come here. This bond will be broken. We'll get a negative charge. Negative will come from the double bond. Double bond will create a negative charge. Negative will come, will form the double bond. Double bond will broken to get the negative charge. So basically, in this structure, you can see that here we will get what? Partial double bond between your carbon and chlorine. So the carbon chlorine bond acquires partial double bond character due to what? Due to resonance. Okay. As a result, the bond cleavage in haloarine is difficult than haloalkane and is therefore less reactive towards the nucleophilic substitution. In case of your alkyl halide, it is a pure single bond. Therefore, nucleophile can easily approach the carbon and halogen. In this case, what happens? It is a partial double bond between your carbon and halogen. Therefore, it is very difficult for my nucleophile to break your carbon-carbon double bond. Okay, and to replace that chlorine, because in this case the chlorine is bonded by the partial double bond. That is one reason. Next is difference in the habitation of the carbon atom in which the
Sir,
halogen is
can
attached.
I
In
repeat
case of your
करो ना?
yes, ये रिपीट करता हूँ, ठीक है। तो बच्चों लोग इसमें क्या होता है, aryl halide does not undergo nucleophilic substitution reaction easily, because if you draw the resonance structure of your aryl halide, you can see that your carbon and halogen atom getting which bond character? Double bond. You can see here double bond है, बराबर ना? In all these cases, because of the resonance effect, your carbon and halogen bond acquires double bond character due to the resonance in case of aryl halide. Okay, and this double bond is called as the partial double bond. Sir, why this double bond is called as a partial double bond? It is formed due to the resonance. Therefore, it is a partial double bond character. ठीक है? And to break this double bond is difficult as compared to single bond. I am comparing this aryl halide with the methyl halide. In case of the methyl halide, what happens? Between the carbon and halogen, there is a single bond. Therefore, you can easily break down that carbon and halogen bond in case of the methyl halide. In case of aryl halide, it is a double bond. Okay, therefore it cannot be easily broken down. Okay, due to tag. Okay, therefore the carbon chlorine bond acquire partial double bond character due to the resonance. As a result, the bond cleavage in haloarine is difficult as compared to what? As compared to haloalkane, and therefore they are less reactive towards the nucleophilic substitution. So nucleophilic substitution आपने देखा होगा, it requires very high temperature and pressure. Okay, then and then nucleophile can approach your halogen. Otherwise, it also requires some electron withdrawing group present at ortho and para position with respect to your halide. Is it clear, बच्चे लोग?
Yes, sir.
इसमें क्या होता है, पार्शियल डबल बॉन्ड होता है बिकॉज ऑफ रेजोनेंस, वो अल्काइल हैलाइड में प्रेजेंट नहीं है. नेक्स्ट है डिफरेंस इन द हैबिटेशन ऑफ द कार्बन एटम इन योर कार्बन हाइड्रोजन बॉन्ड. तो इन केस ऑफ योर aryl halide, this carbon having or halogen attached to this carbon is which bonded or sp2 hybridized carbon. This carbon is sp2 hybridized carbon. In case of your alkyl halide is sp3 hybridized carbon. Okay, so that is the basic difference between your sp2 and sp3 hybridized carbon in case of your aryl halide and alkyl halide. Percentage of S character will be higher in case of sp2 hybridized carbon as compared to sp3 hybridized. Therefore, the bond length will be varying. In this case, it will be lower bond length. Here, it will be higher bond length. Okay. Therefore, as this
Sir,
bond length will be lower, it is a difficult. बोलो
सर हमें कैसे पता
बोलो ना.
चलेगा कार्बन sp2 हाइब्रिडाइज है या sp3?
हाँ, singly bonded carbon is sp3 hybridized. Doubly bonded carbon is sp2 hybridized. Triply bonded carbon is sp hybridized.
Yes, sir.
Okay. So these are the different reasons. That's why your nucleophilic substitution, that means your aryl halides are extremely less reactive towards the nucleophilic substitution reaction. Okay. Next is a replacement of your halogen by the hydroxyl group. So chlorobenzene can be converted into the phenol, but you can see that in this case, this reaction is carried out at a very high temperature, that is a 623 Kelvin and 300 atmospheric pressure. At a, such a high temperature, reaction is carried out. Okay, because of the breaking of this your partial double bond require high energy. Next, you can increase the rate of reaction by adding the electron withdrawing group such as nitro group at para and ortho position halogen atom. The presence of the electron withdrawing group nitro at which position, ortho and para position, increases the reactivity of haloarine. So in this case, you can observe these three reaction. In the second reaction, the temperature is a drop down up to the 443 Kelvin. Okay, reaction other conditions are same, NaOH and H plus. Okay, because of the presence of one nitro group. Next, if I put the two nitro group, one is at ortho and another is at para position with respect to chlorine, and temperature is a further drop down 3, and I will get this product, that is a 2,4 dinitrophenol. समझ में? तो नाइट्रो ग्रुप इज अ व्हाट, इलेक्ट्रॉन विड्रॉइंग ग्रुप, एंड इट विल रिमूव द इलेक्ट्रॉन डेंसिटी फ्रॉम द ortho and para positions. Therefore, rate of reaction of the nucleophilic substitution reactions are increased when the nitro group is present at ortho and para position with respect to your halogen atom. Next is the picric acid preparations. You can treat this compound with the water only or on this compound with the this Cl is going to replace by the OH. So you will get the 2,4,6 trinitrophenol, that is nothing but the picric acid. Okay, and in this case the rate of reaction is increased tremendously because of the presence of the three nitro group which are act as an electron withdrawing group. So my next question is that the effect is higher, or you can call it pronounced, when the nitro group is present at which position? Nitro group is present at ortho and para position with respect to your halogen. So in this case, if the present at the para position with respect to halogen, so what this nitro group will do? So this is about the mechanism wise. There is no need to go in detail, but you can look here. If the nitro group is present at the para position with respect to your halogen, if you draw the resonance structure, you'll get the idea that negative charge is created at which position? Para position. And this negative charge at the para position is a resonance stabilized or stabilized because of this nitro group. Okay. And such a stabilization is possible at ortho and which position? Para position. You can see negative charge is
Ortho
also
and para.
resonance stabilized because of the yes, ortho and para. But such a stabilization is not possible in case of the meta. Okay, therefore, if you put the electron withdrawing group such as the nitro group at meta position, there is no effect on the rate of reaction. Okay, effect is pronounced only in case of the nitro group is present at ortho and para position. Why ortho and para position? Because all of you know that if you draw the resonance structure of your halobenzene, negative charge is going to stabilize. Okay, negative at ortho position by the electron withdrawing nitro group. Similar way, negative charge is stabilized by the electron withdrawing nitro group at the para position. Next is electrophilic substitution reaction. So if you draw the resonance structure of your haloarine, we will get the negative charge at which position? Second position and fourth position. Second position is nothing but called as a ortho position. Fourth position is nothing but called as a para position. Therefore, your haloarine are which directing? Ortho para directing. They are which position? Ortho para. Therefore, if you do the electrophilic substitution reaction, we'll get the two product. One is ortho, another is para product. Why ortho and para? Because if you draw the resonance structure, you will get the negative charge at ortho and para position. That means these positions are electron-rich position. First, we will discuss about the halogenation reaction. In this halogenation reaction, in the chlorobenzene, I am going to add the chlorine in presence of anhydrous FeCl3 act as a catalyst. In this case, basically, I am going to substitute which hydrogen? Ortho and para hydrogen by the corresponding halogen atom. So in this case, I will get the 1,4 dichlorobenzene. In this case, I will get the 1,2 dichlorobenzene. So this is a major product. This will be minor product. Okay, para product will be major in all the cases due to the steric factor and other factors. Nitration. If I do the nitration of the chlorobenzene by using the nitrating and nitration conditions such as HNO3 and H2SO4, so basically I will get the nitro group added on the benzene ring at which position? Ortho and para position with
Ortho and
respect to your
para position.
halogen atom. So this ortho is a minor product, para is a major product. Next is the sulfonation reaction. In case of the sulfonation, I am going to add basically SO3H group, that is called the sulfonic acid group. At which position? Ortho and para position with respect to your halogen atom. So okay, so you'll get this type of product. Other details, IUPAC name and all these things, you can go through that. Next is the Friedel-Crafts reaction. So next is in case of the Friedel-Crafts reaction, I am going to add the alkyl group at which position? Ortho and para positions. Okay, two product. One is ortho, another is para. Out of this ortho and para is a major product. Similar way, next is the Friedel-Crafts acylation. What is acylation? You are going to add alkyl group plus carbonyl. That is called as acyl group. So this type of group you can add at which position? Ortho and para positions. So this is a ortho product and this is a para product. Out of this ortho and para product is major. तो ये सब कंप्लीट हो गया स्लाइड सब. आपको कुछ डाउट रहेगा यू कैन आस्क. कंप्लीट किया. ज्यादा ही फास्ट बोला मैंने. आई थिंक एग्जैक्टली 12:10 हमने स्टार्ट किया था. एग्जैक्टली 1:10 हुआ है. बट ये पूरा की पूरा मॉड्यूल का रिवीजन है. रिकॉर्डिंग स्टॉप करो बच्चे लोग. कुछ पूछना है आपको? कुछ पूछना है आपको?
नो सर.